In this chapter, we extend the linear combination of atomic orbitals to develop the band theory of solids. Let's consider now the wave functions for 3 atoms in a chain. In this case, we start with a basis of 3 atomic orbitals centered at each of the atoms. With 3 atomic orbitals, we expect to find 3 molecular orbitals. The first one is the symmetric molecular orbital with no nodes. Then with 1 node is the first excited state, the antisymmetric wave function with a single node in the very center. Then the last molecular orbital has 2 nodes, where the phase of each atomic orbital is the opposite of its neighbor's phase. If we now plot the energy as a function of separation between the atoms in each of these wave functions, we expect that the wave function with the same phase between each of its neighbors to provide a bonding interaction which lowers the energy of that wave function. In the wave function with 2 nodes with opposite phase between each neighbor, we expect antibonding interaction that leads to a molecular orbital with increasing energy, in fact, the highest energy of the 3. The wave function with 1 node is made up of atomic orbitals from the first and third atom with no contribution from the middle second atom. This means that this wave function has no near neighbor interaction, only a second near neighbor, which is much weaker. We will call this wave function a non-bonding molecular orbital as opposed to the antibonding or bonding molecular orbitals seen before. The weaker interaction makes the energy of this molecular orbital relatively constant with respect to interatomic distance and places the energy in between the bonding and antibonding molecular orbitals. If we now extend this chain of atoms to a large number of atoms, say n atoms, we expect the lowest energy wave function to be the linear combination of atomic orbitals that has no nodes and all of the interactions are bonding between nearest neighbors. In fact, we expect that the difference in energy be due to the bonding interaction of the nearest neighbors in this linear chain that would be 2 near neighbor bonds. Similarly, we expect that the highest energy wave function to be the one with most nodes having antibonding interaction between each of the near neighbors. For a large number of n atoms, we then expect n states with energies between that of the most antibonding state and the most bonding state. For a chain of lithium atoms, the 1s electrons do not get close enough to spread into a band, whereas the 2s valence electrons do get close enough and their energies spread from a bottom of a band determined by the most bonding state to the top of a band determined by the most antibonding interactions. This band, formed from n 2s lithium atomic states, will contain n molecular orbitals that each can contain 2 electrons each. Because a lithium atom has only 1 electron in its 2s atomic orbital, the band of 2s molecular orbitals will only be half filled, with the lower energy bonding molecular orbitals having 2 electrons each, with the higher energy molecular orbitals having no electrons. In this way, we expect lithium solid to contain only non-magnetic spin-paired electrons. As atoms are brought close together, each of the individual atomic orbitals overlap with the neighboring atoms and their energies spread into bands. The outermost and highest energy atomic orbitals overlap first and spread the most. At the equilibrium atomic separation of a typical solid or the normal bond distance, we expect that only the valence electron states have spread into bands, whereas the core electronic states do not interact and all maintain the energy of isolated atoms. High energy states that spread significantly may overlap with neighboring bands, as we see between the 2s and 2p electrons in many metals. In low electronegativity metals such as lithium, these electronic states become close in energy and similar in character to free electron states. In a block band diagram for a metal such as lithium, we would say that the valence electrons of lithium only partially fill up electronic states made up of overlapping energy bands. And that while these states have strong 2s character, they may also contain character of the 2p atomic states and possibly even higher, where the behavior of these electrons may be similar to the free electrons that exist at energies just above the vacuum level. For a typical energy diagram for a metal, we would say that a block of electronic energy levels exists for electrons that are inside the metal, and that these states exist within a band of energies starting from a band bottom and increasing continuously to the vacuum level. The valence electrons of the metal fill up this band starting from the band bottom up to a particular energy we call the Fermi level, or the Fermi energy if referring to temperature 0 Kelvin. For lithium metal, the band edge is 7.2 electron volts below the vacuum level, whereas the Fermi energy is 4.7 electron volts above the band bottom. This leaves 2.5 electron volts as the energy for the highest energy electron to reach the vacuum level, also known as the work function. To recap, electrons entirely fill states at 0 temperature up to the Fermi energy. At any temperature, the average energy required to either add or remove an electron from a system is known as the Fermi level. And the work function is the energy required to free an electron from a metal by bringing it from the Fermi level to the vacuum level. Electrons can be excited from the Fermi level into the vacuum level by light using the photoelectric effect, and this is known as photo-emission. Or an electron may simply absorb additional thermal energy enough to escape the metal, and this is known as thermionic emission. Such high energy electrons may not escape the metal by scattering as something that returns it to thermodynamic equilibrium energy at the Fermi level. Electrons in metallic energy bands are so loosely bound that they can be well described as an electron gas, meaning that to a good approximation they can be described as free electrons. Recall that from the quantum mechanics of a free electron, the energy of a free electronic state depends on the square of its momentum. The lowest energy configuration will have both right moving states and left moving states equally occupied, such that there will be no net drift of electrons either to the left or right. In an electric field, however, electrons will be accelerated from states going against the field to states traveling along the field direction. This asymmetry in the occupation of electronic states will lead to a net drift velocity of electrons. Because it doesn't take much energy to move an electron from a left moving state to a right moving state, metals have very high electrical conductivity. Consider now a metal hooked up to a battery that provides an electric field to the left that pulls our electrons to the right. The electric field must be due to a changing electric potential as a function of position within the metal. The effect of this potential will be to change the energy of our electronic states, simply lowering the electronic energy from one end to the other of the material. Our band of allowed electronic states is then bent from one end of the sample to the other. Throughout the material, the band is still only partially filled with electrons. It is only electrons near the Fermi level that can move into neighboring states that transport from one end of the sample to the other.